We're going to go ahead and work a couple example problems. So this is a quiz from a couple years ago. A 1,000-kilogram car accelerates from rest to 54 kilometers per hour in 4 seconds. The tires have a diameter of 60 centimeters. There's a lot of information I just threw at you, and all of it's mean. And I say that because this is kilometers per hour, this is seconds, this is centimeters. First thing I want to do is probably go ahead and change these into their base units. So 54 kilometers per hour, remember kilometers is 1,000 meters, so 54,000 meters in 1 hour. An hour is 3,600 seconds, so this is 15 meters per second. So that's actually my velocity. The radius, well, I didn't give you the radius, I gave you the diameter. R is half of that, 30 centimeters, but remember that's only 0.3 meters. I'm supposed to find the frequency, we'll come back to that, and the angular velocity. Angular velocity is omega, and omega is how fast this tire is rotating. V is how fast the car is moving. But since the tire has to make rotations to make the car move, this is related. Omega R equals V, which means if I divide both sides by R, I get omega. Omega equals V over R. So if I take my 15 meters per second and I divide it by my 0.3 meters, I get 50, but I get 50 what? Well, this meter cancels that meter and I'm left with per seconds, but that wouldn't make any sense. I'm talking about angular velocity, and a radian is a dimensionless unit, but it keeps track of what's going on. So 50 radians per second is the angular velocity. So omega equals 50 radians per second. Now this is a little bit different. Frequency, remember, is revolutions per second. Revolutions per second. 50 radians is how many revolutions? Well, how many revolutions are there, or how many radians are in one revolution? I want to change this to revolutions. One revolution is 2 pi radians. So this radian will cancel that radian. I'm left with revolutions per second. So if I go ahead and I take 50 and divide it by 2 pi, and be careful if you do that on your calculator because you have to put the 2 pi in parentheses or divide by 2 and then divide by pi. Otherwise it will divide by 2 and multiply by pi. So this gets me a frequency of 7.95 revolutions per second. So frequency is just number of revolutions per second. Angular velocity is going to be in radians per second. B says, give me the linear acceleration of the car and the angular acceleration of the tires. Well, remember, acceleration is change in velocity divided by time. So that's 15 minus 0, final minus initial, divided by, it says 4 seconds. So 15 divided by 4 is 3.75 meters per second. And if I want to change A into alpha, the angular acceleration, remember alpha r equals A, so I'm going to divide both sides by r, and I get alpha is equal to this angular, or this linear acceleration divided by the radius 0.3 again. So we get 12.5 radians per second per second. C down here says, let's go ahead and solve for the distance the car travels as it accelerates and the number of revolutions the tires make while it accelerates. These two things are related. We want a change in position, and we also want the number of revolutions, and we'll come back to that. Remember, I know initial velocity, final velocity, I know acceleration, so I'm going to use v squared equals v naught squared plus twice the acceleration times the change in position. 15 squared equals 0 squared plus 2 times 3.75 times delta x. So 225 divided by twice 3.75 gets me my final answer of 30 meters. So the car moved 30 meters. Now there's two ways I like to think about getting how many revolutions the tires made. First way is to use my equations. Delta x is equal to delta theta times r. Okay, the change in angular position times the radius tells me how far it's moved. So that tells me 30 divided by 0.3 equals delta theta, or how many radians it's turned through, which is 100 radians. This thing is turned through 100 radians. That's not the same thing as revolutions. There are 2 pi radians in one revolution. So if I divide this by 2 pi radians, that implies 100 divided by 2 pi, and remember, if you do that on your calculator, to put the 2 pi in parentheses, otherwise it will divide by 2 and multiply by pi. That gets you 15.9 revolutions. The other way to think about this is the tire is going to roll through one entire rotation, which means it covers a distance equal to its circumference. Circumference is 2 pi r. So if I take 2 times pi times its radius, 0.3, that tells me one revolution covers 1.88 meters. It's got to go 30, so if I take 30 divided by 1.88 meters per revolution, I get 15.9 revolutions. So it doesn't really matter which way you want to think about it. If you want to use radians, then go to revolutions, or go to circumference and then go to revolutions, you're going to end up with the same answer. 2. A rope looped over a pulley is pulled downward at a speed of 4 meters per second. The pulley makes 16 revolutions per second as the rope is pulled. Determine the angular velocity of the pulley and the radius of the pulley. Well, this right here, this 16 revolutions per second, that's a frequency. Frequency equals 16 revolutions per second. Remember, one revolution is equal to 2 pi. So if I say 2 pi radians in one revolution, all I have now is 32 pi radians per second. If you want to look at that a different way, you can actually multiply that by pi and give me the decimal approximation, which is 100.53 radians per second. Then it wants to know the radius of the pulley. Well, this right here is sneaky. We're pulling the rope at 4 meters per second. That tells me V equals 4 meters per second. Right here I have the angular velocity, omega, so I know omega is equal to 100.53 radians per second, and I want to know the radius of the pulley. Well, since V equals omega r, all I have to do is take 4 is equal to 100 times 0.53 times r, divide both sides of this by that 100.53, and I get a radius of 0.039. R equals 0.0397 meters, or if you'd like, you could say about 3.97 centimeters. So pretty straightforward stuff. We're just using the the kinematic equations to solve just like we would in a linear thing, only we're looking at angular things.